All right, for this, we're actually going to start with a couple of thought questions. See if you can remember some things. What will have the largest Doppler shift? A, something that is moving fast. B, something that is moving slow. C, something moving away from us. Or D, something moving toward us. Go ahead and think about it, and we'll discuss in just a bit. So Doppler shift occurs because of relative motion between the source and the observer. How is it that they're moving, towards or away from each other? Hopefully you remember that if two objects are moving towards, then this leads to what we call a blue shift. The wavelengths get squeezed together. If they're moving away from each other, then we see a stretching of the wavelength, which is a red shift. So blue and red shift tell us about toward or away. It doesn't actually tell us anything about the speed, though. The speed is going to be related to the amount of the shift. The faster the object goes, the greater the Doppler shift is going to be. The slower it's going, the smaller the Doppler shift. You can really tell this if you've ever seen a car race. In a car race, the cars can get up to over 100 miles an hour. And when they zip past, you can really hear that change in pitch, which is caused by Doppler shift. As you compare that really rapid change in pitch of a fast car, compare that to something that's going slowly down the road. If it's going slowly down the road, you don't really hear that shift because it's going slow. There's a very small Doppler shift. So the faster the object, the greater the Doppler shift. If it's coming towards, we'll get a blue shift. If it's going away, we'll get a red shift. But how much it gets shifted is all about the speed. The faster it is, the greater the shift. So the correct answer is A. All right, one more because I mean like that. Which planets move the fastest? A, planets close to the star. B, planets far from the star. C, large planets. Or D, small planets. Go ahead and think about it, and we'll discuss in just a bit. So this goes back to Kepler's laws, specifically Kepler's third law. Kepler's third law compares the distance to a planet to how fast it is orbiting, and specifically, the greater the distance, the slower the planet, which means a fast planet is one that's going to be close to its star. The correct answer is A. So the whole reason I bring this up is we can actually use the Doppler shift of a star to figure out if planets are around it. So we don't just have the stars moving in little circles that we might be able to see, but the stars, if it's getting pulled towards us, will be blue shifted. If it's getting pulled away, will be red shifted. So as we look at the spectrum of the stars, we can actually see if it's getting pulled toward and then away and then toward and away and toward and away, and that will then reveal that it's getting pulled around by a star by a planet that is orbiting the star. Now, current techniques using this idea of Doppler shift can actually measure motions as small as 1 meter per second. I realize that those of us who grew up in the United States don't understand what a meter per second means, but that's actually slower, just slightly slower than normal walking speed. So we can literally watch the stars walking because of the pull of planets that are around them. So this method is known as the Doppler shift method, and it's going to be sensitive to very fast moving stars, greater Doppler shifts. Okay, that means that a large planet with a greater gravitational pull, the greater the gravitational pull, the greater the acceleration, the faster the star is going to be pulled around. Second, it's going to be sensitive to planets that are close in. Remember Kepler's third law. Planets that are close in move faster than planets that are farther out, and if the planet is moving faster, the star is going to have to move faster. So it's going to be sensitive to massive planets. The bigger the planet, the greater the velocity, and planets that are close in. The closer in it is, the faster it's going to move also. The very first extrasolar planet ever discovered around a sun-like, by that we mean main sequence star, was actually discovered using the Doppler shift method. This is actually the velocity curve for that star. So up and down we have its velocity. Negative velocity is going towards us, positive velocity is going away from us, and then we're looking at time. So notice from the point where it's coming towards to where it's coming towards again, okay, or where it's at its closest to us, and then here, and then it's closest to us again over here. This shift is 4 days. This planet is orbiting around its star in just 4 days. Then, using the height, how fast it's going, how far it's shifted, we can then determine how massive the planet is. The larger the shift is, the more massive the planet is. Based off of this star, or this planet orbiting this star, is larger than Jupiter. So we have a Jovian planet bigger than Jupiter that is close, incredibly close to its star. To give you a sense of scale, in our own solar system, Mercury is the planet closest to the Sun. It has an orbital period. It goes around the Sun every 88 days. This planet goes around its star in just 4 days. And yet, it's a Jovian. If you remember back to when we talked about the formation of the solar system, where should Jovian planets form? They should be far away from the star, and yet here we have a Jovian planet that is super close in. We're going to have to talk about this more, and we will in a bit. Our third major method that we use to find extrasolar planets is the transit method. The idea of the transit method is if we are looking at the system edge on, then planets will cross between us and the star. When that happens, the planet will block some of that starlight. Now, the bigger the planet is, the more of that starlight it's going to block. So, say if the planet is 0.1% the radius of the star, then we'll see it block 0.1% of the starlight. So what we look at are the light curves. Okay, so up and down, we're looking at the brightness of the star, and then along the bottom, we're looking at time. So at first, we just see the star itself at full brightness. Then, when the planet begins to cross through, it begins to block some of that light. Then through here is when we see the planet crossing all the way. Then, as it gets towards the edge, it starts leaving in front of the star, and so we get the light back until it's back to normal. Okay, this is the idea of the transit method. We actually have the planet crossing in front of the star. Now, it may also be possible to see an eclipse. The eclipse is where the planet goes behind the star. So, it may be possible to see both the star and the planet, although the planet's light is going to be super, super tiny. But it may be possible to actually detect a very slight drop in brightness as the planet goes behind the star as well. The Kepler mission, which ran from 2009 to 2018, used the transit method to find extrasolar planets. It was actually designed to measure the 0.008% dimming of brightness from an Earth-sized planet going around a sun-like star. In other words, it was actually built to help us find Earth-sized planets in Earth-like orbits. Over its 9-year mission, it found over 2,500 confirmed extrasolar planets in 440 star systems. What we mean by confirmed is other methods have shown that they are actually there. It was an amazing thing. About the same time that Kepler ended, a new mission, TESS, was launched, and it is still going, also finding extrasolar planets. I believe to date it's found somewhere around 1,700 planet candidates. Now, there are a couple of other ways we've actually found extrasolar planets. Now, the big ones, the ones that have found the most, are the astrometric, the Doppler shift, and the transit, with transit having found the very most and Doppler shift lagging behind. The fewest have been found with the astrometric, but we have definitely found some. It is a good method. Now, there are a couple of other ways that we've actually found extrasolar planets, although they are less common. One of these is through what we call microlensing. If you remember back when we were talking about black holes and general relativity, we talked about how it is that objects of mass can bend light. This is known as gravitational lensing. Well, something really small is only going to bend light a little bit, so we call it microlensing. So the idea of this method is that we are observing distant stars, and if we have another star cross between us and the distant star, what we'll refer to as the lensing star, then as the lensing star gets into alignment, the distant star's light will actually get focused onto the Earth, so the distant star becomes brighter because of the lensing of the lensing star. Now, if the lensing star also has a planet, and the planet then gets into the right alignment, then we'll see the distant star become slightly brighter again. Now, everything has to work out just right. We have to get everything lined up in just the right way for this to work, but it has found a few dozen planets. The last way we have of finding planets is through actual direct imaging. What this means is we actually take a picture, and in the picture we can see the planets. This method is best done using infrared. Remember, the planets using visible light are only reflecting the starlight, so they're going to be super faint and really, really hard to see compared to the super bright star in the middle. However, in the infrared, if the planet is hot, it will actually be glowing. It will be giving off its own light, which means it's going to be much brighter. And even newer techniques have figured out ways of blocking out the central star. And in that case, it's going to be even easier. It's still not easy, but it is easier to then spot the planet itself. So this is an infrared image. Here in the middle is the star, and over here, this red blob is actually a planet that we've been able to detect.